If you stopped watching this video at one point, then please tell me what the reason was so that I can improve. Otherwise, hi and welcome. I'm trying to learn electrical engineering. Today, measurement of an electric current. And after we've done that, we're going to do extensor carpi ulnar strength training that lies here. And if you participate in the extensor carpi ulnar strength training, then it's better at your own risk. Once having arrived at a reliable value for any particular electrochemical equivalent, we could use this value at any time to measure the size of an electric current. Let's just read it again, not to understand, but to keep it back in mind so that you understand when we're going to read on the next page. Once having arrived at a reliable value for any particular electrochemical equivalent, we could use this value at any time to measure the size of an electric current. All we would need would be an accurate balance and a clock. Okay, there is one advantage and one disadvantage in using this method of measuring current. The advantage is that both the balance and the clock are capable of providing very accurate measurements. I don't know what that balance is. Is that the thing used to look if I don't know the name for it, if a piece of wood is stable or if it's not balanced? Much more so than the usual laboratory ammeter. They're saying a balance and a clock are much more accurate than an ammeter. The disadvantage is that the use of the voltmeter will only give us the average value of a current over some period of time between the two veiings of a metal plate. I mean, with balance, the thing which one is heavier, the thing which justitia head has, the thing to balance that not one is heavier than the other one, which will work in balance. If you weigh how heavy the fruits are, which you buy maybe, but I don't think anyone has seen that one mechanical. Maybe if you go to a market. Now the disadvantage is that the use of a voltmeter will only give us the average value of a current over some period of time between the two veiings of a metal plate. This is not quite as convenient as using an ammeter giving instantaneous values of what might be a fluctuating current. Okay, a voltmeter gives us how much was totally taken, and now we can only say within 10 minutes we have gotten 50 volts or whatever, but when we have the average amount. And an ammeter can give us it is now that, so we have it precisely. With a clock and a balance, however it all works, we can do it more accurate than a voltmeter, than an ammeter, which could give us at any moment, but only for the whole thing like a voltmeter. So the thing is better. It's better to do it with balance and the clock than with a voltmeter. In practice, the readings of ammeters are often checked against current values obtained by using a silver voltmeter. So we're having two at the same time, a silver voltmeter and an ammeter. We're looking what says the ammeter, what is happening right now, and the silver voltmeter, what is happening over the whole thing. And that is just to check if the ammeter is maybe making some errors. The following example will make the calculation clear. A current deposits, that is the thing we're talking about. A current deposits 4.0248 grams of silver in 2 hours. If the electrochemical equivalent of silver is 0.00118 grams per column, what is the average value of the current? Mass deposited equals electrochemical equivalent times current in amperes times the time in seconds, and that makes sense. This equation can be rearranged as follows. Current in amperes equals mass of silver deposited divided by the electrochemical equivalent of silver times the time in seconds. The time must be expressed in seconds because 1 ampere equals 1 coulomb per second. So that, okay, another thing back. Electrochemical equivalence. Now I know what we're talking about. That was the previous part. It was about how much of an element like silver can be transported with 1 coulomb of current in 1 second or something. Now, in Faraday's first law of electrolysis, it states that the mass of a substance liberated during electrolysis is directly proportional to the quantity of electricity passed through the electrolyte. So we're letting current from one thing to another going, and it takes every time a bit of silver with it. It's now in a silver solution with a silver block to another part of silver. One thing is the anode, the other the cathode. So the current is running from here to here. And from the silver block, it is taking no silver into the silver liquid over to the other side. And now some silver out of the silver liquid goes to the other silver thing. And the amount of silver taken from the block into the liquid and from the liquid to the other silver block is directly proportional to the amount of current put onto the anode transported to the cathode. So 1 coulomb of electricity brings so much silver over to the other side. 1 coulomb of silver brings 0.001118 gram over to the other side. If you put 1 coulomb of electricity onto that silver block, it will put 0.0018 gram of silver into the current, into the liquid, and also 0.0018 gram of silver per second onto the other silver block. And the whole amount deposited is the same as the electrochemical equivalent, and the electrochemical equivalent is with 0.00118. With silver it is 0.00118, the amount of silver transported with 1 coulomb of electricity over to the other side. For copper it is 0.0033, or for oxygen 0.0000829. Is it possible to transport oxygen with electricity? Is it possible to give a diver through an electric cable oxygen? No, don't attempt that. I don't really know what I'm talking about. Okay, the mass deposited is now the electrochemical equivalent, which is 0.00118, times the current in amperes. So how much we have, how much current is taken on it. So how much is totally deposited onto it depends on how easy this silver is going, on how easy that element is to be transported. Some are very hard to transport, others easier. And silver is transported with 0.001118 gram over to the other side. So we're having the mass deposited equals how much can be transported, or how easy is the transport to silver, nickel, copper, oxygen, times how much current in ampere is, so how much current we're putting on it, times how long we have it all running. So it's how easy bring we it over, how strong are we pushing it over, and for how long. And that is how much we have brought over. This equation can be rearranged as follows. Current in amperes equals the mass of silver deposited divided by the electrochemical current of silver times per second. It makes sense, you can just turn it out. All these mathematical things. So if you want to know how much current, how much force was put onto it, we just, because it's always the same, the first law says it is always proportional. It will be always with 1 coulomb, 0.0118 grams silver transported over to the other side. If you put it here from the anode to the cathode, I still don't know if it's anode, cathode, or cathode anode. The current comes from the anode and goes through the silver liquid to the other cathode. The current is just running from the anode to the cathode. So just for the basics, it was missing. And every time it runs, 1 electron runs basically 1 coulomb of electricity running over to the other side takes 0.00118 gram of silver. Silver over. Okay, and the current we have put onto it equals the whole mass of silver now deposited onto the other side, so brought over, divided by how hard was it to bring it over, and for how long have we tried it. So it's just math, you just turn it around. The time must be expressed in seconds because 1 ampere equals 1 coulomb per second. So that the current equals 4.0248, that is the whole amount of gram we have brought over. In 2 hours we have brought over 4 grams. Divided by how easy was it? It was 0.001118. Could we bring over with 1 push? times 2, because for 2 hours, times 60, because every hour has 60 minutes, times 60, because every minute has 60 seconds. So times 7,200. Or a half ampere. Because we have 4,000 gram brought over. No, I don't know how we come to it. At one time, the international ampere was defined as a current of such a size that it would deposit 0.00118 gram of silver per second. In this way, a current was defined by its chemical effect, although this definition was replaced some years ago by one using the magnetic effect of the current. Okay, they're saying 1 ampere is the amount of 1 coulomb of current. I don't know what it exactly. Current is, as far as I understand it, just the amount of electrons going from one side to the other. And 1 coulomb is, I don't know what it's, let's say it's 8 billion. 8 billion electrons going over. And if you have the power of 1 ampere, you're bringing 1 coulomb over per second. So if there's 1 ampere, you're bringing, or imagine 8 billion electrons over to the other side. And then the other thing, if it would be nice to have it to know, but maybe I'm going to make a separate part just on coulomb to know it. And if electricity is actually just electrons going to the other side, because it would make it so much easier. It could be something people can imagine. It are just 8 billion, whatever, electrons going through our silver liquid to the other one. And that's making 0.00118 gram of silver with them. That sounds totally logical. It's no magic. It's just electrons going to the other side and taking them with them. That was the electrical engineering part. If you were here for electrical engineering, you can go directly to the next part of electrical engineering. If you stay here and participate in the extensor kappa and strength training, that is with the arms. Go to step stance. Arms next to us with fists, and they bring these fists down, holding it, banging it up. The floodgate exercise. Again now. 3 rules. Rule number 1. If there's pain, stop immediately. Second rule. Go only as far as it goes with a little bit of effort. Rule number 3. Don't overdo it. We just want to strengthen the muscle, not to exhaust it. Next exercise. Hands from the fists and bring them up. And down. The counterfeit money check. Done. Now, you can use, instead of a sock, also a towel or a t-shirt. Have it just and press with good force onto it. Now bring it again down. And back. Press evenly with all 5 fingers. We want to train the extensor kappa nerves. So press with the 4th and 5th finger equally. Other side. Press with good or moderate force. Again up. And last time up. Other hand. Press and bring it to the outside. Other hand, press and inside. And now press hard from the top and bring down. And again. One more time. Down. Upper hand, press and again down into flexion. To extend. Last time down. Now hold just good in the middle. And the other side. Press. And this was it. Oh, one more exercise. Let's do the claw. Go with moderate force over the middle part of the lower arm. That is where the extensor digitorum muscle is. Not the extensor kappa nerves, but whatever. And on the other side. Okay, that was the extensor kappa nerves strength training. Thank you very much.